This is the syllabus. I have completed this basics and LTA system. Now I'm going to start this topic, this continuous stem Fourier series. CTFS, continuous stem Fourier series. To start this topic, first I will explain the vectors. The vectors concept. I have a three-dimensional plane, X, Y, and Z. Okay. So the directions are represented by unit vectors. The unit vectors are used to represent the directions. Right? So along X, you have AX. Along Y, you have AY. Along Z, you have AZ. Right? So these unit vectors are used to represent the directions. Now these three vectors are AX, AY, AZ are unit vectors. That is, their magnitudes are 1, right? Their magnitudes are 1. And one more condition is there, is they are mutually orthogonal. If these two conditions are satisfied, then those vectors are called as orthonormal. Orthonormal vectors. Right? And we have a three-dimensional plane, right? We call it as a three-dimensional vector space. When I discuss linear algebra topic, all these things will be cleared. But I'm explaining these things very briefly. This is AX bar, AY bar, AZ bar. These are AX, AY, AZ, right? This is a three-dimensional plane I have taken. That is a three-dimensional vector space. And I also have three vectors, right? AX, AY, Z. And these three vectors are also orthogonal. AX dot AY equal to 0, AX dot AZ equal to 0, AY dot AZ equal to 0. Because these three are mutually orthogonal, their dot product is 0. So I have three-dimensional vector space and I also have three orthogonal vectors. Then this set is called basis. We have three-dimensional plane, that is a three-dimensional vector space, and I also have three vectors. The number of vectors in the set is 3. That is number of vectors in the orthogonal set. This is called orthogonal set. I also have three vectors, that is equal to dimension of the vector space. Then this set is called basis. These vectors are called basis vectors. Okay, if I have these basis vectors, that is the number of vectors equal to the dimension of the vector space, and they are mutually orthogonal, then I can represent any vector, let us say some f bar, as a linear combination of these three vectors, these three orthonormal vectors. Suppose any vector f bar in that vector space, f bar in that vector space can be represented as the linear combination of these three orthonormal vectors. Suppose it has an x component, some fx along x direction, and fy along y direction, and fz along z direction. Then this vector can be represented as this linear combination of these three orthonormal vectors. Now, how to find out these coefficients fx, fy, fz given f bar? I know f bar, right? How to find out these coefficients? That is important. See, this f bar is there, then I will do a dot product ax. I will get fx ax plus fy ay fz az dot product with ax. Then what you get? ax dot ax1, that is fx, plus ay dot ax is 0, az dot ax is 0. This is f bar dot ax. You will get fx. So to get x component of f bar, we need to dot product with ax bar. Similarly, to get y component, we need to do dot product with ay. You will get y component of f bar. Similarly, we need to do dot product with az bar with f bar. Then you will get fz. Right? This is important. So I have explained these basics of vectors very briefly. I will explain when I discuss linear algebra. So here I have ax, ay, az as basis vectors. That is, they are mutually orthogonal, and the number of vectors are also equal to the dimension of the vector space, or the vector space is nothing but here the three-dimensional plane. That's it. Okay, it is vector space. Similarly, now come to signals. From signals point of view, I will take some orthogonal signals, that is 1 cos omega naught t, cos 2 omega naught t, cos 3 omega naught t, and so on, sin omega naught t, sin 2 omega naught t, and so on. This is a signal space, orthogonal signal space. All these signals are orthogonal to each other. Okay, so I will give a proof for this. They are orthogonal. See, I will take two signals, any two signals from this. I want to prove these two signals are orthogonal. So first I want to define the orthogonality condition for signals. Okay, but for vectors the orthogonality condition is that dot product must be 0. Right? If their dot product is 0, then these two vectors are said to be orthogonal. Ay dot az also 0, ax dot az also 0. So they are mutually orthogonal vectors. So the dot product is defined like this for vectors. For signals, so let us say x1t and x2t are two signals. If they are said to be orthogonal, their inner product x1 to x2t, this is inner product. This is defined as integral of 0 to t over one time period x1t x2 conjugate t must be equal to 0. This is inner product. If it is 0, then you will get two signals x1t and x2t are said to be orthogonal to each other. So this is defined like this. Okay, now I want to check whether these signals given in the signal space, this is the orthogonal signal space, this one, whether these signals are mutually orthogonal or not. First I will check one condition. First I will check these two signals. Let us say 1 and cos omega naught t. So x1 of t is 1, and cos omega naught t is another signal, and if conjugate it you will get same cos omega naught t because it is a real signal over one time period 0 to t. We cannot take minus infinity plus infinity because cos is not defined for t is minus infinity plus infinity. Okay, so that I am taking capital T. Yes. What do you get? Sin omega naught t by omega naught, where t is 2 pi by omega naught, 0 to t. T is 2 pi by omega naught. Then 1 by omega naught. Substitute capital T. in place of small t, you'll get 2 pi by omega naught, you'll get sine 2 pi minus sine 0. Sine 2 pi also 0, sine 0 also 0. So you'll get 0. So this 1 and cos omega naught t, these two signals are orthogonal to each other. And I will take one more pair. Okay. I will take some cos 2 omega naught t and sine some 3 omega naught t. Okay. This is x1t, this is x2t. Now their inner product x1t, x2t, integral over one time period capital T 0 to t. What is x1t? Cos 2 omega naught t. x2 conjugate t, you will get sine 3 omega naught t, because it is a real signal. You will get x2 conjugate t is x2t only. The t is 2 pi by omega naught. Now I will multiply and divide with 2. 2 sin a cos b, sin a plus b, sin a minus b, sin a plus b plus sin a minus b, cos 5 omega naught t by 5 omega naught minus cos omega naught t by omega naught 0 to t. Right? Here minus 1 by 2 omega naught. Now substitute capital T. T, whether t is 2 pi by omega naught. Then you will get cos 2 pi by omega naught here. In place of t, 2 pi by omega naught. What do you get? Omega naught cancel. You get cos 10 pi. Next, substitute lower limit here itself. Minus cos 0. Right? Next. Thus, in this signal, in place of t, 2 pi by omega naught, you will get cos 2 pi minus lower limit 0, cos 0. Okay. Cos 10 pi is 1. Cos 10 pi is 1 and cos 0 also 1. And cos 2 pi is 1, cos 0 also 1. So 1 minus 1, 0, 1 minus 1, 0. You will get the entire 0. Right? So these two signals are also orthogonal. We will take one more integration. I am taking, let us say, two signals, which is cos n omega naught t and cos n omega naught t. Both are same signals I am taking. Okay. Both are same signals. Then I will integrate it. Cos n omega naught t into cos conjugate of n omega naught, you will get cos n omega naught. I'm just integrating them. What I will get, just checking over one period 0 to t. What do you get? Integral 0 to t cos square n omega naught t. So this can be represented as 1 plus cos 2 n omega naught t by 2, this dt. Now here 1 by 2, this is t, this is sine 2n omega naught t by 2n omega naught 0 to capital T. Now 1 by 2, substitute capital T here. This is capital T, and here sine, in place of t, substitute capital T. You will get 2 pi by omega naught. You will get omega naught cancel. Substitute t here, you will get 2 pi by omega naught cancel. Sine 4 n pi, right? Sine 4 n pi. Next, substitute lower limit minus here. In place of t, 0, plus in place of sine 0, 0, and sine 4 n pi also 0. Sin n pi is itself 0, sin 4n pi also 0. Now you will get 1 by 2 into capital T, right? So if you integrate these two signals, which are both same, in place of n, you substitute 2, cos 2 omega naught t and cos 2 omega naught t, you will get some constant which is t by 2. It is not 0 because these two are same signals, not orthogonal signals. These two signals are not orthogonal signals. Okay. If cos 2 omega naught t and cos 2 omega naught t, these two are not orthogonal signals, right? If 2 is not there, so if in place of n some m is there, right? Some m, then these two are orthogonal signals, which is also important to find the coefficients. Okay. Now I have orthogonal signal space, which is 1 cos 1 omega naught t, cos 2 omega naught t, cos 3 omega naught t, and so on, sin omega naught t, sin 2 omega naught t, and so on. This is orthogonal signal space I have. Then I will represent any signal xt which is periodic with period is t, that is 2 pi by omega naught. Okay, this is the condition for x of t. X of t must be periodic with the period t, which is t equal to 2 pi by omega naught, where omega naught is the fundamental frequency of the signal x of t. Then this x of t can be represented as same the linear combination of all these orthogonal signals. So this one is there. So this coefficient is, let us say, a naught into 1 plus some a1 into cos omega naught t. These are coefficients, right? So like fx, fy are represented there. Here, this is f bar, this is ax bar, ay bar, az bar. These are orthogonal signals. This fx is coefficient. Fx is along ax bar. Fy is component of f bar along ay bar. Fz is component of f bar along az bar. Similarly, there also a0 is coefficient in the direction of 1. A1 is coefficient in the direction of cos omega naught. Similarly, A2 cos 2 omega naught plus and so on. Some B1 sin omega naught plus B2 sin 2 omega naught plus and so on. These are infinite summation. These are not just finite summation, these are infinite summations. So this entire thing can be represented as, now this x of t be represented as a naught summation sigma n equal to 1 to infinity some an cos n omega naught t plus summation sigma n equal to 1 to infinity bn sin n omega naught, right? This is called the Fourier series representation. The condition here is x of t must be periodic with period capital T. T is 2 pi by omega naught. If I have a signal periodic with a period 2 pi by omega naught, I can represent this x of t as sum of this orthogonal signals. So this is cos omega naught is one orthogonal signal, cos 2 omega naught is one orthogonal signal, and so on. Sin omega naught is sin 2 omega naught and so on, right? So cos omega naught t, a1 cos omega naught t plus b1 sin omega naught t. This is the fundamental frequency component. Similarly, cos 2 omega naught t plus sin 2 omega naught t. A2 cos omega naught t plus b2 sin 2 omega naught t. This is second harmonic. X of t is a naught plus a1 cos omega naught t plus b1 sin omega naught t. This is called fundamental component, fundamental frequency component of x of t, and b1 sine t, a2 cos 2 omega naught t plus b2 sine 2 omega naught t. This is called the second harmonic of x of t, and so on. Okay, you can represent x of t as sum of all harmonics, sum of all its harmonics, infinite harmonics. Okay, now how to find out these coefficients, this a naught, a1, b1, a2, b2, a3, b3, an, bn, right? How to find out it? Now this is x of t, a naught plus sigma n equal to 1 to infinity an cos n omega naught t plus sigma n equal to 1 to infinity bn sin n omega naught t, right? So I have already explained in the, so to find out this fx, this is fx. To find out this fx, we did inner product with dot product with ax bar here, this one, right? To find fy, this one, we did dot product with ay bar here also. To find fz, we did dot product with az bar. Similarly here, to find this an, to find this a naught into 1 is there here, and to find bn, what I do, so I will do their dot product here. In case of signals, we have to do inner product. I will do inner product with, okay, I will do inner product with 1. So first I want to find out a naught, so here I have 1. I will do inner product with 1, inner product of x of t with 1, okay, throughout the equation. Here also inner product with a naught with 1 plus sigma n equal to 1 to infinity inner product with an cos n omega naught t into 1 dt here plus sigma n equal to 1 to infinity integral of bn sin n omega naught t dt. Anyway, you multiply with 1, you will get same signal. So here over one period t, 0 to t, 0 to t, 0 to t, 0 to t, right? Here you will get a naught into t. Here if you do integration, you will get a naught into capital T now plus, but this terms, right? Here we need to first expand the summation. Suppose if n equal to 1, okay, a1 cos omega naught t, if you integrate over one period, a1 cos omega naught t will get 0. That I have already derived here. Here integration of 0 to t cos omega naught t will get 0, right? If you substitute cos 2 omega naught t, integration of cos 2 omega naught t will get 0, sin 2 omega naught t will get 0. Anyway, you will get 0 only, okay, because those are orthogonal signals. Okay, so here 1 and cos n omega naught t are orthogonal signals. Here sin n omega naught t and 1 are orthogonal signals. So if you integrate them, you will get 0. Okay, this term is 0, this term is 0. It will 0 to t x of t dt. From this, a naught equal to 1 by t integral 0 to t x of t dt, right? This is the important formula a naught, because this a naught is the special case of cos omega naught t, cos n omega naught t, where n equal to 0, 0 into omega naught, that is no frequency. This is a DC component. Zero frequency component is also called as a DC component, right? So a naught is a DC component, or sometimes also called as average value. Similarly, I want to find out an also. I have x of t is a naught plus sigma n equal to 1 to infinity an cos n omega naught t sigma n equal to 1 to infinity bn sin n omega naught t. So I want to find out this an, right? To find an, what we have to do? We have to do inner product with this cos n omega naught t throughout the equation. So inner product with x of t cos n omega naught t with within the limits 0 to t. Then what do you get? So here first a naught is there, a naught into 1 is there. So a naught into 1 into cos n omega naught t dt plus sigma n equal to 1 to infinity an will get cos square n omega naught t here, cos square n omega naught t dt plus sigma n equal to 1 to infinity bn sin n omega naught t cos n omega naught t integral of 0 to t. This 1 and cos n omega naught t are orthogonal signals, so you will get 0. Their inner product is 0. Here also sin n omega naught t cos n omega naught t are orthogonal signals, their inner product is 0. It's also 0. But here an cos square n omega naught t. I have already derived this. We will replace cos square n omega naught t by 1 plus cos 2 n omega naught t. Here I have already derived. I'll show you. Here cos n omega naught t cos n omega naught t. Cos square n omega naught t. Cos square n omega naught t. You will get t by 2, right? Integrate this signal cos n omega naught t and cos n omega naught t. You will get 1 by 2 into t for one period. That I will replace here. an into 2 by t. Sorry, an into t by 2. You got here this one. an into t by 2. That I have already derived there. From this, an equal to 2 by t integral 0 to t x of t cos n omega naught t dt. This is an. Okay. Similarly, you will get bn. You just need to do inner product with sin n omega naught t. This one, sin n omega naught t. Do inner product with sin n omega naught t. You will get bn. That I will write here. Bn is 2 by t integral 0 to t x of t sin n omega naught t dt. That's it. I will write down all the formulae. Suppose I have orthogonal signal space, that is 1 cos n omega naught t sin n omega naught t. This is orthogonal signal space where n is ranging from 1 to infinity. Okay. Then I can represent any signal x of t with a period capital T. Period capital T, that is 2 pi by omega naught. Then x of t can be represented as a naught into 1 plus sigma n equal to 1 to infinity an cos n omega naught t plus sigma n equal to 1 to infinity bn sin n omega naught t. So these coefficients, how to find out these coefficients? This a naught that I have already derived, that is 1 by t integral 0 to t x of t dt an 2 by t integral 0 to t xt cos n omega naught t dt bn 2 by t integral 0 to t xt sin n omega naught t dt. So this is how we need to find out a0, an, bn, right? Here we need to find out these three integrals, right? To represent this x of t as a sum of orthogonal signals, we need to find out these three integrals. So first you need to find out a0 and then an and then bn. Then you have to substitute them in the equation, right? This is a0, an, and bn. Okay, this is a real Fourier series or a trigonometric Fourier series because we have trigonometric functions sine and cos. That is why this is called trigonometric Fourier series. And we don't have any complex numbers here. That is why it is also called as real Fourier series, right? That's it.